Welcome to Lesson 3, Lewis diagrams for ionic compounds. The lesson objective, construct Lewis dot diagrams for ionic compounds. Recall that an ionic compound occurs between a metal and a nonmetal, where the valence electrons from the metal are transferred over to the nonmetal. And so in order to construct these dot diagrams, these are just representations of what is actually occurring. We want to take our ion dot diagrams that we constructed in our atomics unit, and we're simply going to place them next to each other, representing the ionic bond or our ionic compound. And we want to make sure that the total ion charges add up to 0. So for example, in magnesium chloride, if you look at magnesium, it has a charge of +2. And therefore we need 2 chloride ions because each one has a charge of -1. So the whole thing then adds up to 0. And this will match our chemical formula for magnesium chloride, which is MgCl2. Recall that our dot diagrams for our positive ions, all positive ions, our metals, are going to be the element symbol, our brackets, and no dots, representing a loss of electrons, and of course a positive charge, whatever that positive charge may be. And for the negative ions, in this case the nonmetals, it's going to be the symbol always going to have 8 dots representing the full valence shell, and then a negative symbol depending on what that may be. So let's look at an example here, what is actually going on. So we have sodium chloride, our ionic compound, our metal, our nonmetal. And so if you look at the sodium atom, it has 1 valence electron, as it's in group 1. And then the chlorine atom has 7 valence electrons, as it's in group 17, it's a halogen. And look at the electronegativities. Sodium is a 0.9 and chlorine is a 3.2. So this atom has a much greater attraction for electrons, and in essence it's going to take the valence electron from sodium. There's a transfer of that electron over to chlorine. And so since chlorine is gaining an electron, it's gaining an extra negative charge. We put the negative 1 charge outside our brackets, indicating that it's an ion and it has a charge. And notice that it has the 8 dots around the symbol. And then what happens to sodium? Well, when it loses its electron, it's losing a negative charge. So it has more protons than it does electrons, and therefore, since it lost 1 electron, it becomes positively 1 in terms of its charge. And then we have lost that valence electron, and that's why there are no dots on any of our metal ions. Now, what forms the bond? Because in a covalent bond, they were sharing these electrons. It was equal pull holding them together. Well, what's holding these things together is this positive and negative charge. This is an ionic bond. It's an electrostatic attraction between these 2 charged particles. Let's look at the dot diagram of calcium chloride and see how it's formed first. So calcium has 2 valence electrons, and chlorine has 7 valence electrons. And if you look at the electronegativities, they're similar to the previous example. Calcium has a electronegativity of 1, and of course chlorine is 3.2 as before. So the chlorine atoms have a much greater attraction for electrons. So this chlorine is going to take 1 of these electrons to complete its valence shell, and it's going to form the -1 ion. And then another chlorine is going to take the other valence electron and complete its valence shell, and now that forms the other -1 ion. And since calcium lost 2 valence electrons, it now has a +2 charge. And you see that's why we have 1 calcium with a +2 charge and 2 chloride ions with the -1 charge for each one. If you add up the total charge, you'll see it equals 0. -1 and -1 is -2. +2 equals 0, and this has our ionic bonds occurring because of that electrostatic attraction. Okay, so let's just see, how do we just simply construct these dot diagrams? Well, let's look at barium sulfide. So the first thing you want to do is you're going to locate barium. Here's the element box, and you see it has a +2 charge. And so we're going to draw that dot diagram first. Because it's a metal, it's a positive ion, our cation, it has no dots, just our symbol, our brackets, and our charge of +2 as indicated in the upper right corner of our element box. And then for sulfide, that is sulfur. Sulfur is written last in the name, so therefore it has to be the anion, the negative ion, so it's always going to be that top number. And so we're going to write our negative ion. All negative ions will always have the 8 dots, the brackets, and the charge. Make sure you're writing the -2 charge here. And now we check, does the total charge equal 0? +2, -2, yes, it equals 0. So that is the completed ionic dot diagram of barium sulfide. Now I want to show you actually what is really going on and why this is forming. So if you look, barium has 2 valence electrons. That's a group 2 alkaline earth metal. And the sulfur atom has 6 valence electrons. And so this is a much more electronegative element, so it's going to take those 2 valence electrons to complete its valence shell. It's a transfer of electrons, and that's why it's ionic. It's transferring electrons from the metal to the nonmetal. And so when the sulfur gains 2 electrons, 2 negative charges, that's where the -2 charge is coming from. And since barium loses 2 electrons, it now has more positive than negative, and so it has 2 extra positive charges compared to the negative charges. Or you can think of it as having 2 less negative charges. And of course, this attraction here is our ionic bond occurring between the positive and the negative, and that's an electrostatic attraction. Let's look at one more example, aluminum oxide. So aluminum has a +3 charge, and so I'm going to draw that ion dot diagram. Again, it's a positive ion, so no dots. And then oxygen is a -2, so I'm going to draw that. That's our anion, so that's going to have 8 dots, brackets and charge. And you notice that the total charge does not equal 0. And so we're going to keep adding ions in order for this to equal 0. Right now we have 1 extra positive charge, and so I'm going to bring in another oxygen to gain more negative charges. And so now I have -2, and -2 is -4. We have +3, so now I have too many negative charges. So I'm going to bring in another positive charge. That gives me +6 on my aluminum, but only -4 on the oxygen. So I need 1 more oxygen to get this to equal 0. So -2, -4, -6, +3, +3 is +6. This whole thing equals 0. So this is our completed Lewis dot diagram for aluminum oxide. And this is why the chemical formula for aluminum oxide is Al2O3. And we can see what's really going on behind the scenes is that each aluminum has 3 valence electrons, and so you can see where they're being pulled into or transferred into the oxygen atoms to complete their valence shell. Let's check your understanding. Can you construct Lewis dot diagrams for ionic compounds? At this point, you should be able to construct Lewis dot diagrams for ionic compounds.